Okay, hi everybody. I'm going to give you a series of pre-lab lectures on Lewis structures. I know this is a new topic for many of you, so it'll be a little bit longer, but I'll try and break it up into some smaller segments so it's digestible. I usually like to start with this slide. I don't know if anyone is familiar with this movie. It's by a director named Stanley Kubrick. When you're in college, you should watch Stanley Kubrick movies. It's called How I Learned to Stop Worrying and Love the Bomb. And one of my goals for this lecture is that after it, you might change that to Lewis structures. I'll be honest with you and tell you that I think most students don't particularly like Lewis structures because they're confusing and the rules for generating them are obscure. And I think this quote sort of sums it up kind of well. It's from a German scientist, and he was talking about thermodynamics, but the same thing applies to Lewis structures. He says thermodynamics, or Lewis structures or whatever, it's a funny subject. The first time you go through it, you don't understand it at all. The second time you go through it, you think you understand it, except for one or two small points. The third time you go through it, you know you don't understand it. But by that time, you're so used to it, it doesn't bother you anymore. Maybe this is your first time looking at Lewis structures, and you'll be confused, right? That's okay. Maybe this is your second or third time going through it, and you think that you've kind of got it, except for one or two small things. And maybe after the end of this, you'll go through it and realize that you don't get it at all, right? I'm actually in this third category. I've gone through this more than 3 times, and I still get Lewis structures wrong. But I'm so used to it now that it doesn't bother me, right? Lewis structures involve a lot of chemical intuition, and that's okay, right? You won't be perfect the first time, but I hope to help you understand how we use these in chemistry. So Lewis structures are named after this guy, Gilbert Lewis. He's one of the most famous chemists of all time. The basis for Lewis structures is the so-called octet rule. And the octet rule is a basic statement that each atom in a molecule likes to have a total of 8 electrons in its valence shell. Right? So we're going to try and get groups of 8 electrons around an atom. And so one question you might ask right away is, well, what's a valence shell? And here's my definition. Qualitatively, I would say that valence electrons are the ones that are available to form bonds. These are the ones that we can make bonds with. More functionally, the valence electrons are the ones associated with the row of an element. So one thing you'll definitely want to do in this lab is get out your my papers all close. Get out your lab manual, and in the back there's a periodic table. Okay, find that, and you sort of look across the row. More technically, these are the electrons which are in the outermost shell, right? The largest n quantum number. So with that, I'm going to get into it. There are a set of steps for generating Lewis structures, and here's the first one. The first one is you have to figure out the number of valence electrons that are in the molecule. Again, for neutral atoms, we count to the right of the next closest filled noble gas configuration. If I have an ion, I'm going to add or subtract the number of electrons which are equal to the charge on the ion. And a quick hint, if you do this and you get an odd number of electrons, you probably did something wrong. This is actually an incredibly important step. If you have the wrong number of valence electrons, your Lewis structure is absolutely wrong, right? It turns out it's actually hard to get a wrong Lewis structure, but this is one way you can do it. So I'm going to give you some examples, if I can get my pen to work. There you go. The first one is methane, CH4. Here's carbon right here, right? Z equals 6. The next closest filled gas is helium, the noble gases. So when I count its valence electrons, it has 1, 2, 3, 4. Carbon has 4 valence electrons. Hydrogen, right, it has 1. There are 4 hydrogens, so 4 times 1 equals 8. There are 8 valence electrons in methane. Example 2, carbon dioxide. Again, carbon is here, so 1, 2, 3, 4. Oxygen is here, So 1, 2, 3, 4 at carbon, 5, 6 at oxygen. And again, there are 2 of them. 4 plus 12, I'm pretty sure that's 16. And here you can start to see these multiples of 8 coming into play. I mentioned that if you have an ion, you add or subtract electrons. So an example would be ammonium, NH4 plus. Ammonia is up here. 1, 2, 3, 4, 5 valence electrons. Hydrogen, again, has 1. There are 4 of them. And this is a positive ion. It's a cation, so I've lost an electron, and I'm going to subtract 1. This equals 8. Cn minus, 4 here, 5 here, 4 plus 5. This is an anion, a negative ion, so I've added an electron. This one gets 10. Okay, as I mentioned, if you get an odd number of electrons, you probably did something wrong. Once you've done this, you are going to organize your atoms in a 2D arrangement, so they're positioned next to a bonding partner. This is sometimes called a skeletal structure. So some quick notes. Electropositive atoms are near the center. Electronegative atoms are near the edge. Hydrogen always has one bonding partner, and it is terminally located. Hydrogen is never in the middle. And I gave this hint here, or is it, there are actually some odd molecules that break this rule. And lastly, use your woman's intuition or your sense of symmetry. Right? Molecules have a high degree of symmetry, and your intuitive sense of the beauty of the molecule will come into play. So let's go back to this one, CH4. If you were to guess what these atoms might be arranged like, you might guess something like that. Carbon in the middle, hydrogen's around the edge, right? CO2, oxygen, carbon, oxygen. Once you've done that, step 3, I need to place electrons between the molecules to form bonds. These are called bonding pairs. And I distribute the remaining electrons in pairs around atoms to achieve an octet. We draw these as 2 dots. Right? These are called lone pairs. Bonding pairs are shared between atoms and count towards the octet in both members. Lone members are associated with a single atom and only count towards the atom on which they're located. So methane, CH4, you will recall that this had 8 valence electrons. Here is my skeletal structure. And now I have to start putting electrons, my 8 valence electrons, around this atom. And so you simply go 1, 2, 3, 4. Again, each single line here represents a pair of electrons, a bonding pair. So this carbon atom has a total of 2, 4, 6, 8 electrons in its valence shell, and its octet is met. Hydrogen, you'll notice, only has 2 electrons in its valence shell, and that's the way hydrogen always works. Right? It's always terminally located. It will always violate the octet rule. Carbon dioxide, CO2. This one had 16 valence electrons. We drew it like this: oxygen, carbon, oxygen, and away we go. I start putting electrons in between it. 2, 4. Now I'm going to draw lone pair electrons, and these lone pairs we draw as single dots. So 2, 4, 6, 8, 10, 12, 14, 16. 16 valence electrons, so I can only put 16 electrons in the molecule. And I count this up. I'm going to switch my color here. This electron, again, a single bonding pair, 2, 4, 6, 8. Carbon, 2, 4, 6, 8. These electrons are both happy. If I look at this carbon, 2, 4. This one only has 4 electrons in its valence shell. It is very sad. Boop, boop, boop. Okay. What do? If you can't achieve an octet around an atom, what you do is move lone pairs on a terminal atom so they become shared bonding pairs. Right? And now rather than a single line, we will have 2 lines, which we call a double bond. There are 4 electrons in a double bond. Or 3 electrons, which is a triple bond. Right? So going back to carbon dioxide, I had originally drawn it this way, carbon, right? And one more. Again, not a filled valence shell over here. So what we're going to do is take and move one of these bonding pairs into a double pair. And I'm going to move one of these into this one. And if I do that, here's what I can end up with. So now I have 2 double bonds between the carbon and oxygen atoms. That's 2, 4, 6, 8 electrons. I got 8 more to go. So I start filling up the lone pair electrons. 2, 4, 6, 8, 10, 12, 14, 16. Total of 16 valence electrons. The oxygen here has 2, 4, 6, 8 electrons. It's happy. Carbon, 2, 4, 6, 8 electrons. It's happy. Oxygen, 2, 4, 6, 8 electrons. It's happy. This is the Lewis structure for CO2. All right, I'm going to stop here and I'll show you my next video.